All right, chapter 5 is polynomial functions, or chapter 5, all of chapter 5 is polynomial and rational functions, but 5.1, polynomial functions. Now, much of what I'm going to touch on in 5.1, I still consider review from previous classes, although there might be something just a little, presented just a little differently here. So it's important to go over it. All right, so let's look at some examples. And let's start off with this notation that will haunt you if you don't sit down and figure it out. All right? It'll haunt you all book, all semester long. All right. So everyone is familiar with ax squared plus bx plus c. That's just the letters of the alphabet that we typically use to talk about a quadratic equation. But there's a different way to talk about it, especially when you haven't predetermined exactly what degree you'll be working with. In other words, this works great for degree 2, but I could change it to a sub 2 x squared plus a sub 1 x plus a sub 0. And if I did that, the whole quadratic formula would change. Instead of starting with minus b, would start with minus a1. But hopefully you notice what's going on here is the subscript of the a's, of the coefficients, matches the exponent or the degree. So the convenience of this is if I wanted to talk about a larger function and I just wanted to add another term, I could call it, I know what I'm going to call it. I'd call it a sub 3. It's possible you'd run out of letters of the alphabet if you went with this A, B, C strategy, but you can always use subscripts. So the first term is going to be referred to as a sub n x to the n. And the next term, this is kind of number line thinking that, you really do have to understand it. If I have a number line, and this is the point n, the point after that would be n plus 1, and the point before that would be n minus 1. I mean, not a deep idea, but that's what's going on here. If this is a sub n, the next one down would be a sub n minus 1, a sub n minus 2. Hopefully you get the idea. This a sub 0 plays the role that c played in the quadratic. And you just have to get used to this notation, either with an actual number in it, like a sub 3, or a letter in it, like n. I do refer to this as number line thinking. So on a number line, when you talk about an arbitrary point, you should know the points before and after that arbitrary point. And that's what it takes to understand this. All right, so just a change in notation that you might not be used to. But these are polynomials. And one thing important about the polynomial is that, as we're going to find out soon, the exponents have to be counting numbers. The exponents have to be, well, essentially x to the 0, x to the 1, x to the 2. Otherwise, it's not a polynomial, it's some other type of function. So here's an example, identifying a polynomial. And let me go ahead and take this a little further than they did here. They just say this is the leading term, this is the constant term. So when I say take it a little further, I'm going to say what this means to us is a sub 3 is 4. A sub 2, do you see it? It's negative 1/2. And I should say literally a sub 1, you don't see it, since there is no term with x to the 1, so a sub 1 must equal 0. It's invisible, but we can think of it as a 0x in here. And of course, a sub 0, also known as the constant term, is negative 7. And again, what I was saying is you can think of this term as 7x to the 0. Remember, x to the 0 is 1. Anything to the 0 is 1. But the x to the 0 is invisible, but that's why this term gets the name a sub 0. Another polynomial, not in proper order. I suppose it helps to put it in proper order. And it is a polynomial, again, with the leading term corresponding to the term with the highest exponent. You can identify those. Constant term is a common question. Hopefully you know that we can change this to, and we'll cover this directly in a topic, but you can change this to x to the 1/3, and fractions in the exponent are allowed. Now, fractions in the coefficients were fine. We saw that earlier. We saw a term that was minus 1/2 x squared. Nothing wrong with having a 1/2 for the coefficient, but you can't have a fraction for the exponent and still call it a polynomial. So, not a polynomial. This is one polynomial divided by another polynomial. It has a name. It's called a rational function, but it's not a polynomial. I should say a word of caution. If the rational function actually reduced and it was no longer a fraction, well, maybe it could work into a polynomial, but a quick glance would tell you that this would not reduce into, even if I could factor it and try to cancel, it wouldn't reduce completely into a polynomial. So, not a polynomial, it's something different. Technically speaking, this is a polynomial of degree 0, meaning I can think of it as 9x to the 0. It's a polynomial. Even without multiplying this out, we should know it's a polynomial. We know what happens when you square this. You get something that is a polynomial. You multiply it by x cubed, you get another, it would still be a polynomial. You might even be able to figure out without writing all this down that it would have been a polynomial of degree 5. And this kind of thing where you predict not just a sub n, but what n is, and a sub 0 is exactly what we're going to be doing in the future. So maybe without, well, that's exactly what they did. They found out that n was 5, the degree was 5. The first coefficient was -1, invisible 1. And the constant term is 0. And those are things that, you'll be asked directly and in some cases indirectly about a polynomial. When I say indirectly, what I mean is it might be factored and it might not be in its polynomial form like this. But you should be able to find those things just by kind of, I guess, predictive multiplication. If you can just kind of predict what would happen if you did the multiplication, at least for the first term. There's no way to predict what's going on kind of in the middle. Like the 6 might not have been easy to see, but just that being squared, that being cubed, kind of tells you that's a 5. So it's just a tip that I want you to hopefully see that. All right, and then they give us this table. You're going to see a linear function in a way you're not used to. You're used to mx plus b, but they're trying to embrace the notation of the chapter. This is not what you're used to. You're used to ax squared plus bx plus c, but again, if you embrace the notation of the chapter, you'll see it a sub 2x squared plus a sub 1x plus a sub 0. And they always do this. They talk about calculus. All right. So in calculus, there's actually not just we don't just deal with functions that are what we call smooth and continuous. We have a way of measuring how smooth and how, not how smooth, but how well, I guess, how bendy a graph is. So calculus is in the business of, finding turning points and measuring things. But notice how this kind of looks like I just took a rope, a stiff rope, maybe even a wire, and just bent it without breaking it, without kind of cracking it. It's what we call smooth and continuous. This right here, this corner right here, that would not be considered smooth, and this gap or this hole would not be considered continuous. So the idea here is, even if you have no idea what a graph looks like in detail, you know that polynomials will look something like this because they must be both smooth and continuous. You can draw it without lifting your pencil, and you don't have these cusps or bends or corners in them. And smooth and continuous is the actual words they use in calculus. All right, we have something called the power function, and that's just a single term, just a monomial. And they're telling you that you should be able to use some tricks to graph a power function. Now this idea, I'll talk about it again a little bit later, but the way I like to introduce this idea of end behavior is when we're graphing, we're actually interested in how the graph leaves the box. Just something, probably the simplest graph of this kind, maybe not the simplest, but y equals x cubed. Kind of looks like a half parabola going this way and a half parabola going this way. And these little arrows right here are kind of a nod to what comes in calculus, and that is you need to know how the graph leaves the box. It leaves the box in quadrant 1, it leaves the box in quadrant 3, and calculus is just as interested in how the graph leaves the box as how it appears inside the box. That's what end behavior, and that's what all this arrows and this infinity is talking about. Like, what happens at infinity? What happens when it leaves the box? And what happens indeed? All right. When you have an odd graph, let's look at some examples. When you have an odd graph, let's see, and a positive a value, like this one, the graph's going to leave the box in quadrant 1 and quadrant 3. And we might have talked about this before. When you put a minus sign, what happens is the graph changes quadrants. Specifically, if you put a minus sign and you have an odd graph, it's going to change from leaving the box in quadrant 1 to leaving the box in quadrant 2 instead of quadrant 3 to leave the box in quadrant 4. I'm not going to talk about that right now, but touch on it here. All right. If you have an even exponent, like 2 or 4, the graph's just going to look like this. This looks a lot like a parabola. It's a little flatter and it goes up more aggressively, but when I say it's like it, it's that kind of U shape we're familiar with for parabolas, and it leaves the box in quadrant 1 and quadrant 2. If I shift it in a predictable way, add 1, shifts it 1 to the left. If the box is big enough, in other words, if we're talking about this going to infinity, it's still going to leave the box in quadrant 1 and quadrant 2. Other things, what are they doing? Oh, multiplying it by 1/2. That is a vertical compression. I don't think you'll ever have to graph something in this much detail for something like this, but just the idea is helpful. And they're going to talk about this. We'll talk about this on the next video.